but then then 3/4 of the final will be the other three sections. So we'll have the stoichiometry, we'll have the activity series, and so on 75% of the final. But on 25% of the final will be this last part, the Lewis dot structures and hybridization and orbital shapes and all of that stuff. So that's right. Okay, so then next week. Okay, so next week I'm going to be gone on Wednesday and Friday. I've got some things in Fort Worth with my mom, some doctor's appointments and things. So I'll be trying to make some videos. But what we're going to do is we're going to probably swap the MO theory stuff and the Vesper shapes. I'll tell you what, I'm going to do I'll do some videos on Vesper shapes for while I'm gone, okay? On Wednesday and on Friday that you guys can watch. And then I will share with you some videos on MO theory that are actually from my PChem class that I have. And we're going to emphasize in this class the Vesper shapes is what I'm calling. I know you don't know what that is yet, but that's what we're going to emphasize in this class because that's the skill you need more for the follow-on courses if you're going on to organic and things like that. So we'll really focus on the VSEPR theory, the Vesper shapes of the molecules, the 3D shapes of the molecules. And so I'll put those MO theory videos up. And then when I come back, it says on the schedule, like the Monday of Thanksgiving week, we'll be talking about MO theory. But I'll be really drilling you on the Vesper shapes to make sure you guys understand that. And then we'll have MO diagrams the week after Thanksgiving, and I can hit those. So just be ready. I'll communicate with you on Blackboard about the plan for next week on Wednesday and on Friday, and I'll have some videos loaded up to Blackboard for you to look at. Do not take the week off, right? We've still got Alex things to do, and so on. So there's that old maxim: when the cat's away, the mice will play. Don't be a mouse and don't play. Even though I'm gone, you got to stay working and stay with the course because you don't want to end poorly. You want to end strong. Okay, so let's do that. So Alex reports, good job for those who have started tonight's homework. All right. So let's jump in. There's some really important concepts today, so I'm really glad to see you all here. We're going to be talking about formal charge. We do the Lewis dot structure, and then there's some structures where we have choices in how we make them. And formal charge is a way to guide our choices. So formal charge is a really important concept. Resonance is an important concept. So we're going to talk about resonance. And then we're going to start dipping our toes in the deep end of the pool when we get to organic chemistry. So we're going to learn a little bit about organic molecules today and some bigger molecules for our Lewis dot structures. So don't be intimidated by that. It's really just bigger molecules. And when molecules get more complicated, we need more vocabulary words to describe them. So we're going to learn about alcohols, acid groups, amines, and things like that for the different chemical groups. This was left off the last one. We didn't get through the notes, but I just wanted to make sure that we hit this. That we talked about electronegativity last time. Here's the electronegativities showing that fluorine is the most electronegative. It's got a number of 4, electronegativity of 4, and here cesium is the least at 0.7. And so here, let's look at lithium. Lithium is 1, and fluorine is 4. So this has a sort of a negativity of 4, right? 4.0, and this has a 1.0. And so this end of the molecule is really negative. So in practice, we draw an arrow towards the negative side of a molecule, and we put a little plus on the end of that arrow. So it's a little arrow with a plus on the end. The plus shows the positive side, and the arrow is pointed towards the negative side of the molecule, and that's called a dipole. Okay, and we draw those dipoles on our polar molecules. And here's HF, so hydrogen. So hydrogen's 2.1. It's better than lithium in terms of electronegativity because it's above it, but it's still 2.1 versus 4. And so we still have a dipole, but it would be a shorter arrow if we were to draw it, where the magnitude was the difference between those two. And look at the colors. These colors come from a software package called Gaussian, and this is called an electrostatic potential map. And it's if we walk around the molecule, how positive is it where we're standing, or how negative is it where we're standing? And so this is sort of, and they did the colors. So red is negative and blue is positive, and you can see that this molecule has a bigger red-blue difference than this one, showing that lithium fluoride is a much more polar bonded molecule than hydrogen fluoride. And what do you get with fluorine? With the two atoms, the two F atoms are the same, right? You have a 4.0 on this side and a 4.0 on that side for electronegativity. It's all green. There's no red part, there's no blue part. So that would be nonpolar. So this is the phrase that we need to learn. Nonpolar versus polar. So when we have molecules that maybe have polar bonds, let's look at boron trifluoride. Let's just do this as an example. These are all 120 degrees apart. Now this is a very polar bond. This bond has a dipole moment that's pointing towards the fluorine. And this one has a dipole moment pointing towards the fluorine. And this one has a dipole moment pointing towards the fluorine, right? And so even though each individual bond is polar, because those bonds are 120 degrees apart, the molecule as a whole is nonpolar. So that's the only time it gets confusing about polar and nonpolar. We talk about molecules being polar or bonds being polar. So there's two different things, right? You got to pay attention. We're talking about the bond. The BF bond is polar because F is negative, the boron is positive. But the molecule as a whole, because the bonds are 120 degrees apart, you can kind of think about, would this be a stable arrangement if those bonds were bungee cords? Right? The boron would snap in the middle and there would be 120 degrees there, and those three polar bonds are all pulling on that boron. And if you walked around the whole molecule, you wouldn't ever find a positive part of the molecule and a negative part on one end or the other. So it would be a nonpolar molecule. So that's the only time it gets confusing. So here's, and what does this mean by dipole? Well, it's just like a battery, right? The battery has a positive end and a negative end electrostatically, and that's what we're talking about, a molecule. And so we would draw this little arrow pointing towards the negative end with the plus on the end that's positive. So you'll see those things in science and in chemistry. So let's look at these kinds of deals in ALEKS. This was the last set of homeworks where you're looking at this. You have two chlorines bonded together, and of course they're the same atom, and so we would say this highlighted bond is nonpolar. Here we've got bromine, which is negative, and hydrogen, which is positive, so you've got a dipole moment going like this. And so then the highlighted bond is polar, and the more negative atom is bromine. And then here we've got a nitrogen and hydrogen. I don't know, I don't need to really look up to see how negative nitrogen is, but I see that nitrogen is up in the corner over there, hydrogen is not. And so this is a polar bond, and the more negative atom is nitrogen because it's more close to fluorine. Yes? Is that any scenario where the more negative atom is just like... The only one is like the hydrides. And so if we have lithium hydride, so think about the name. This is lithium. Normally we have like hydrogen fluoride, hydrogen chloride. What is the IDE telling you? It's telling you that's an anion, right? A negatively charged thing. So when we have a metal hydride, the IDE is telling us that that's an H minus and a lithium plus. So there the hydrogen is acting like the anion, and we actually saw that in the previous screen. So this is pretty cool that you notice that. Here's lithium hydride. And this is a plot of the size of the electron cloud. So notice how the lithium has got a tiny little ball, and the hydrogen has all of the electron density on it. And so that's the H minus and the lithium plus. And then hydrogen fluoride, hydrogen's got a smaller electron cloud around it, and the fluoride has a big one, so it's the F minus and the H plus. So that's the only case would be hydrides. Okay, now we get into formal charge. So this is on tonight's homework, this concept of formal charge. So I've written the procedure up here in gray. And so this is the procedure for calculating the formal charge. And it is kind of controversial because it's the way I think about it. Okay, it says write down the valence electrons for that atom. Okay, so we have a Lewis dot structure that we start with. We write down the valence electrons for that atom. So we're putting on little charges on every atom in the molecule. Okay. And then we subtract the number of electrons the atom can claim in an equitable divorce. Okay, that sounds controversial, but we'll see what I'm talking about. And then the result is the formal charge. So let's do this for this molecule. And so we've got this oxygen here. And so it's got 6 valence electrons. Is everybody clear with that? Oxygen, 6 valence electrons. Okay. Now, what do I mean by this equitable divorce? Every bond, they're going to split equally. They're like, all right, we're done. You take an electron and I'll take an electron. Okay. So then this is how many it can claim. So every bond, you get 1 electron because we're splitting it with the other one. So oxygen comes in. It's got 1, 2, 3, 4 for its lone pairs. Those are on it. So it's their oxygens, lone pairs. They're oxygens, electrons. But then when the bonds, that's what we're splitting up. I hate divorce, so I hate using this analogy, but it works. Okay, so we got 2 electrons there from the bonds. So we have 6 claimed electrons. And so we end up with 0. So this has a formal charge of 0. 0 formal charge. And you can save yourself a whole lot of work by just recognizing things, right? If we split these together, this oxygen looks the same as the one we just did, doesn't it? Everybody see that? And so every oxygen that has 2 lone pairs and 2 bonds is going to have a 0 formal charge. So you can really do this quickly once you start recognizing patterns. And so this oxygen has a 0 formal charge. Now this whole molecule is +1, so we're going to have to find a plus somewhere in this business. Okay, so let's look at the nitrogen now. How many valence electrons for nitrogen? Look again at the periodic table. Yeah, that's okay. That's all right. That's all right. 5 valence electrons. Okay, and then if we split them equally with all their neighbors, nitrogen comes in with 4. And so we end up with +1 formal charge. And I don't know why, but they always, just when we write these little charges, we always put the number in front. So it's or we could just put a plus. But if it was like 3 plus or 4 plus, we put the 3 positive charges. But that's where so this is kind of showing that in this molecule, the positive charge is really on the nitrogen, not on the oxygens. So that's kind of nice. So that's formal charge. Any questions? Okay.
Is always going to be splitting up.
Just, yeah, so you get to claim your lone pairs, like oxygen starts out with 4, and then it starts splitting those bonds. And it gets 1 electron from each of the bonds. So that's what I mean by the equitable divorce, right? They're like, all right, you take an electron, I'll take an electron. Don't think of them as kids, that's not good. But think of them as property, right? We got 2 cars. You take a car, I'll take a car. Okay. So let's practice. Okay, so let's use this is why we like formal charge. So let's use the octet rule for this molecule, and it's got a charge too. So for the sulfur, let's calculate the valence electrons. We have 6 valence electrons for the sulfur, plus 4 oxygen atoms, and oxygen has 6 valence electrons each, and then plus 2 more because of the charge. You see where all of the pieces come from. All right. So 4 times 6 is 24, plus another 6, so we got 30, so we have 32 electrons. And please check my math. If I ever make a mistake, you get a sticker if you identify it. So that's the first step. Second step was to make single bonds. So we put that molecule together with single bonds. So we've used up 2, 4, 6, 8, minus 8. We'll call it Be for bonded electrons. Okay. 24 electrons left over. And so we've got 4 oxygen atoms. 4 times 6 is 24. So we just put 6 on each of those oxygen atoms. So each oxygen has an octet. That's great. Oxygen's more electronegative than the sulfur, so this makes sense too. Okay, so that's 24. NBE for non-bonded electrons. Down to 0. We're done. Check octets for oxygen, nitrogen, carbon, fluorine. And the oxygens have octets, and the sulfur has an octet. So sulfur looks like argon. Oxygen looks like neon. Everybody's happy. We're done. Oh, not quite. I always forget this part, don't you? Okay, put a bracket and put a 2 minus. All right, so now we're done. That's the octet rule, Lewis dot structure for sulfate anion. Now, we're going to take this same structure and we're going to calculate the formal charges. Okay, so let's just rewrite it over here. One, 2, 3, 4. This is so tedious to make all these dots. It's tilting, I don't know why. Okay, so let's look at this. So oxygen comes in with 6 valence electrons. Okay. And then how many does it claim? Well, it's got all those lone pairs, 2, 4, 6, plus 1 for the bond. So 7, minus 7 claimed. So it's a minus 1 formal charge. So look at that. All 4 of those oxygens are the same kind of oxygen. All right, so we've got a minus 1 here, a minus 1 there, minus 1, and a minus 1. So we got 4 negatives in this molecule, all the different oxygens. Okay, it's kind of a problem because we have a 2 minus up here, and yet we've calculated 4 negatives. So let's do this sulfur. It comes in with 6 valence electrons. Just check that with the periodic table. You see sulfur's under oxygen, so it's the same number of valence electrons. And then how many can it claim? It gets 1 for each of those bonds. Yeah, so it can only claim 4. And so this is a plus 2 formal charge. And that's kind of cool. 2 plus. So we got the 2 plus minus 4 gives me a negative 2. So that's great. Everything works out. And those are the formal charges for this. But think about it realistically. If I'm looking at this molecule, am I really going to be able to keep something that's positive 2? Am I really going to keep those negative electrons? The oxygens have more electrons than they really need. And yeah, they have an octet, but they could share 2 more electrons and get rid of that plus 2 charge. Does everybody see that? So you got a plus 2 right next to 4 negatives. And sulfur's a big atom. So it can have an expanded valence. It can share more than just 8 electrons. So let's go ahead and cancel that plus 2 by sharing some electrons. So if we share these 2 right here, we'll redraw our Lewis dot structure now with formal charges being minimized. And we have 2 different types of oxygens now. So we know this type of oxygen is a -1. Okay. So that has a minus charge on it. That has a minus charge on it. The sulfur, let's do that one. So it comes in with 6 valence electrons. And how many can it claim? If you just look at that. Yeah, so it's got 6 bonds, and it gets 1 electron for each bond if in an equitable split. Okay, so it can claim 6. And so it has a 0 formal charge. That's beautiful. So this one is charged 0. And then this type of oxygen here, we know that oxygen brings in 6 valence electrons, and it can claim 6. In fact, that's the same kind of oxygen we saw on the previous slide. It has 2 lone pairs and 2 bonds, and that's got a 0 formal charge. So we got a 0 here and a 0 here. So this is a molecule that has a lower set of formal charge numbers, meaning they're all closer to 0 or 0. So this is the preferred structure using formal charge as a guide. This is the structure if you just stick with the octet rule on everything. Okay, so I prefer this one. This also shows me why if I were to add protons to this, I could make sulfuric acid, right? So H plus and H plus here. This negative charge, those electrons could donate and make a bond to the hydrogen here, or to the cation, and make sulfuric acid. And so that's kind of a way to think about the chemistry too. You've got a formal charge on an atom. You got a formal charge on an atom. Positives and negatives attract. And so I could see how I would make a sulfate anion into sulfuric acid, H2SO4, following the formal charges. So we really like these. Resisting the urge to yell. Okay. Can I clarify anything about this to anybody? What? Pretty straightforward. Okay. Now this is, Alex will have you make some molecules, but it's sort of the background knowledge you need to complete all the little sub pieces on Alex. Yes. Let me see. I'm trying to think. These are some of the. I don't know. I'd have to go back and look to see. Yeah. If they're talking about using formal charge to produce the structure, they'll want this one, right? So. Yeah. So let's look at some of the Alex type problems where we recognize some wrong Lewis dot structure. So there's different ways, or say there's different levels of learning. Okay, if I just give you a list of things to memorize, that's a pretty low level learning. That's just listing things. Okay, then you get to construction or building. This is a building skill. This is a little bit higher in terms of difficulty. There's decision making, like in stoichiometry, trying to find the limiting reactant. You've got to do some problems to figure out and decide which is the limiting reactant. So that's a little higher. Recognizing errors is even higher. And so these next problems may give you some trouble, okay, because they're more of a critical thinking and evaluation skill. That's pretty far up the chain of learning skills, is recognizing problems. And so here we are in these types of Alex problems. It's saying decide whether the Lewis structure that's proposed for each molecule is reasonable or not. Okay, so what is reasonable? Things like octet rule for C, N, O, and F. Okay, and other things, or the valence electrons are right, and so on. So this is it's giving you some prompts. Are the number of valence electrons wrong, or do the atoms have the wrong number of electrons around them, and so on. And it's having you identify the problems. And so here we're looking at this molecule. First, let's let's see if the total number of valence electrons is wrong. So we've got 2 oxygens bringing in 6 apiece, so that's 12, plus the 4 from carbon. So 12, 13, 14, 15, 16. Okay, 16. So we got 2, 4, 6, 8, 10, 12, 14, 16. So, okay, we've got 16 electrons. That seems reasonable. Do some of the atoms have the wrong number of electrons around them? Okay, so, oxygen can claim 8. Carbon can claim 8. This oxygen can claim 8. Even though this is a really bizarre structure, it looks like it would be reasonable. Okay. It's probably not. If we were to do the formal charge on this thing, we would see that this is a minus, this is a 0, and this is a plus. Okay, and so you're not going to be able to keep that minus and plus apart. We're going to have electrons flow, from the minus over to the plus, and so we would correct that using. But yes, it is a reasonable structure. It just has a high set of formal charges. Let's look at this one. Okay, so the chlorate anion. So chlorine has 7 valence electrons, plus 3 times 6, plus 1. All right, so 3 times 6 is 18, plus another 8. Okay, 18 and 8 is 26. Okay, and so let's add them up. So we got 6, 6 there, 6 there, 18, 19, 20, 21, 22, 24, 5, 6. We only have 26. Okay, so that's good too. We have 26. So we have the correct number of valence electrons. And now let's look to see if the atoms have the wrong number of electrons around them. So this would be, again, looking for the octet rule violations. This oxygen has 8 electrons around it. Same with the other one. Chlorine has 8. But look at this guy. 2, 4, 6, 8, 10. So this one's bad. So we would mark this one in Alex. No, some atoms have the wrong number of electrons around them. The symbols of the problem atoms are, and it's oxygen. So you would just type an O there. And they have a little note on Alex. If, let's say, the 2 oxygen atoms had wrong numbers of electrons, you would put O twice. So you say oxygen and oxygen. They're looking for, the symbols of all of the atoms that have wrong electrons around them. And if there's 2 of them that have oxygen, or maybe even 3, you would just put O that many times. Yes.
Is chlorine supposed to have 7 valence electrons?
That's this one right here, 7.
Oh, okay.
Yeah.
Okay.
Yeah.
But in the drawing, it has 2, 4.
Yeah, in the drawing, it has 8 around it, which would be good, in which to have an octet at least. Chlorine can have more because it's in group 3 or below.
Okay.
Yeah.
That's right.
Yeah.
So to make this correct, would you move one of the lone pairs to the top of the chlorine?
Yes. Mm-hmm. Yeah. So that was a good question. So to fix this one, we would make this one a single bond and put a lone pair on there like that. Yeah. Yeah. And in which case that would be a chlorine, it brings in 7 and it can claim 5. So it's going to be a +2 on the chlorine. And each of these is a -1. -1, -1, and -1. And so, yeah, putting the lone pairs on chlorine, leaving all the oxygens in the -1 configuration would give us the overall charge right there. Okay. Now, we might be able to reduce those formal charges by making double bonds. So we would move these oxygens down and those lone pairs down and form double bonds to the chlorine. And then the chlorine would have a 0. These 2 oxygens would have 0, and we'd have 1 oxygen with a -1 charge on it. But we'll do that. We'll do some of those weird ones later today. Okay, so here's just some more of this. This is ozone. So 3 times 6. There's 3 oxygen atoms, so 6 valence electrons each is equal to 18. Let's add them up. 2, 4, 6, 8, 10, 12, 14, 16, 18. So it's okay with this one. This oxygen has 8. This oxygen has 8, but how many does the one in the middle have? 2, 4, 6, 8. Okay, it's good too. So I think that's a reasonable structure. PF4 minus. So we have phosphorus with 5 plus 4 times 7 for the fluorines. 4 times 7 is 28, 29, 30, 30. Oh, and plus 1. I was like, I'm getting an odd number. Plus 1 for this charge right here. Okay, 34. Okay, and so we've got, let's just look at the rounds of fluorine. We have 8 around this fluorine here, and there's 4 of those. So 4 times 8 is 32. And so it has the wrong number of valence electrons. The correct number is 34. Did I do that right? 4 times 7 is 28. 28 plus 5 is going to be 33. Plus 1 is 34. So it should be 34. And I looked at this Lewis dot structure and I only see 32 electrons. So how would we fix that structure? We would put the remaining 2 on the phosphorus. And that would be the correct structure for that. So phosphorus has 10 electrons around it, which is okay because phosphorus is in group 3 and can handle it. Okay, so now let's do some weird ones. So these are the weirdest Lewis dot structures you'll find, kind of like the ones we just saw with that phosphorus and so on. So let's look at BrCl3. So we have 7 valence electrons for bromine, plus 3 times 7 for the chlorines. So that's 4 times 7, or 28 valence electrons. So we're going to put the Br in the middle. 2, 4, 6. So we've used up 6 bonding electrons. We have 22 left over. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Minus 18. And so we've got 4 left over. So these are NBEs. And we got 4 more non-bonded electrons. We can't put any more on the chlorines. They have an octet. We stick the rest of them on the largest atom there in the middle. And so we make a couple of pairs. I got them kind of separated a little bit like that. So that's BrCl3. It's kind of a T-shaped molecule. What about Br3 minus? Okay, we have 3 times 7 valence electrons plus a 1 for the minus. So that's 21 plus 1, so 22 valence electrons. All right, we'll just stick all 3 atoms together. What else are you going to do? That uses 4. Okay, so we have 18 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm just going to put the rest of them on the middle atom. So 13, 14, 15, 16, 17, 18. So crazy molecule, lots of electrons all bristling on that thing. This would be a very good reducing agent. It's going to want to give those electrons to something, okay? Let's do the xenon ones. So we say that noble gases don't react, right? You've heard that. I mean, they don't form chemical compounds. And xenon says, hold my beer, right? It's ready to go. It's just got so many electrons so far away that if you put it with an electronegative element like fluorine, they'll snatch one and they'll make a bond. So the fluorine is so electronegative, it's like, yeah, okay, xenon, these electrons are far away from the nucleus, so you might not notice, and I'm going to bond with you. So we have some xenon fluoride compounds, and sometimes with oxygen too. So this is kind of strange. So we have the 8 valence electrons for the xenon, plus 4 times 7 for the fluorides. Okay, it's not charged, so we don't add any extras. So here we go. 4 times 7 is 28, and then that gives us 36 total. So we're gonna, I'll just draw it small over here. Xenon and fluoride. Two, 4, 6, 8. We've used up 8 electrons. All right, we're back down now to 20, 28. So I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Non-bonded electrons. And I got 4 left over. So where do they go? Well, they got to go on a central atom. I mean, that's it. That's all that's left. So we'll put another 2 on there. And this molecule is, when we actually look at the structures of these Lewis dot structures do give us some knowledge of the shapes of the molecules. And so those lone pair electrons are going to want to get as far away from each other. So they might go on the top and bottom of the molecule, and this molecule turns into a square planar molecule. It's a planar molecule with all the fluorines and the xenon in a plane. And so understanding how the electrons go on the molecule gives us insight into the shapes of the molecules. All right, let's do this one. So we have 8 for the xenon, plus 2 times 6 for the oxygen, plus 2 times 7 for the fluorine. Okay. So 2 times 6 is 12, plus 8. That's nice. That gives us 20. And then we have another 14. So that'd be 34. Okay, 34. I'm going to put the fluorines as far away as possible because they're like little balls of negativity. They're going to just get away from each other. And I'm going to put the oxygens. Oops, I can't do that. Away from each other. So I've used up 4 bonding electrons. Okay, and then we're down to 30. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't do it. I'm bumping into my little tools down here. Come on. Let me do it. That's so ugly. 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Is that right? Oh, is it 8? Yeah, 2, 4, 6, 8. Thank you. Very good. Very good. All right, give that person a sticker. All right, you found an error. I tell you, if you find an error, who was it? Okay. All right, so let me erase the math here. Okay, so now we're down to 26. Is that right? 26. And then we used
24 to 24.
Yeah, minus 24. Thank you. Okay, and so then we have 2 left over. Yeah, and so then we put those on the central atom. And so that's this molecule. When we get to the Vesper shapes, we'll rebuild it, and we'll notice how all those electron pairs will repel each other, and this one kind of turns into a seesaw structure. So we have like a square planar for XeF4, and then for XeF2O2, we have a seesaw. I don't know if y'all know what a seesaw is. Back in the day, we had this thing that was a board balanced on a pivot, and it was dangerous. Man, it was fun, though. Yeah. You seesaw with somebody, and you would always ask them, make them promise, no offs. You know what that means? They get you in the air, and then they jump off. And then you go, bam, and That's probably why I have a compressed back problems, because we jumped off the seesaw with each other all the time. And in our park too, to make it more strong, they had an extra board underneath the middle that didn't go all the way. And if you got too, like sometimes when you got a heavy kid and a light kid, the heavy kid had to cheat up a little bit. And so a lot of times I was the heavy kid. So I had to scoot forward. But if you got your hands in the wrong spot, that board would crush your fingers. Oh man, this is a very dangerous toy, but it was great. So this is fun when I see the seesaw structure, which we'll get to later. It's just glorious. Okay, so let's see. Here we have this last one with all halogens again. So the iodine, we have 7 plus 5 times 7 for the fluorines, right? So just connecting all of those. All right, so what is that, 42? I'm doing well with my math today. Okay, so then let's put the iodine in the middle, and we'll put 5 fluorines around this. Okay, so 2, 4, 6, 8, 10. Minus 10 bonded electrons. 32 left over. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And so those are the non-bonded electrons. And so then we have 2 more that we stick on the central atom. So that's our IF5 Lewis dot structure. Oh, let's go back over here to this one, the seesaw, my friend. And let's calculate the formal charges on this dude. Okay, so this fluorine, if you think about it, it's got 6. It brings in 6 valence electrons, but if we break it, let me do blue so we can just do it right on the molecule. Okay. Right, so if we break that bond right here, then fluorine, it brought in 7. It has 6 in the non-bonded plus 1 in the bond. So it's got 7 that it can claim. Does everybody follow that logic? Good. Okay. So it's got a 0 charge on it. This fluorine is the same, 0 charge. Okay, xenon. So if we bring in 8 electrons for the xenon, how many can it claim? Well, it's got a lone pair, so 1, 2, and then 4 bonds, 3, 4, 5, 6. So it brought in 8, and it can claim 6. So it's a plus 2 charge. Okay, 8 minus 6. So this is a plus 2 on the xenon. What are these oxygens? This type of oxygen, it's got a single bond and 6 in the lone pairs. It brings in 6 and it's got an extra, right? So it's a minus 1 type of oxygen. So if we were to minimize the Lewis dot, minimize the formal charges on this, then we would start sharing double bonds with the xenon. So it would look like this. And then we'd have those extra lone pairs on the xenon. So that's our xenon dioxide difluoride molecule with the formal charges minimized. Okay, yes?
If you have 3 minus, would you still have to put
Yeah, very good. Well done. Okay, so another mistake caught. Let me put the brackets up here. I told you I always forget those brackets. So we're going to put a bracket here and do a minus. Nicely done. Okay.
So the middle element really never, or middle atom never really breaks the octet rule when you put extra on it, correct?
It's definitely breaking the octet rule. Yeah, and it really is only going to work for group 3 below. Like you can do this with the chloride, the bromide, iodide, and then xenon, and so on. So those are the big atoms. They're in the middle, and then chemistry can happen out at the frontier because, for like a bromine, that's out in Utah, if the nucleus is in Huntsville. So Huntsville has no idea what's happening in Utah. Okay.
So why is that? Why does it start in 33
because they're big enough to have 10 electrons around them or 12 or
So
whatever.
it just has to do with the
It's just the size of the atoms, yeah. So the second row, carbon, nitrogen, oxygen, fluorine, they won't do this. You won't have extra electrons on that central atom. Yeah.
You do the alkali metals too, all those that come through below.
Okay, good question. Where are the metals in all of this, right? These are all the covalent molecules that we're making with carbon and oxygen and everything like that. So when you get into metals, then you're back into the ionic bonding, and you have not covalent electrons, but ionized. They're stealing the electrons from the metals. Yeah. So this is really all of the non-metals that we're exploring now for these molecules. So now resonance. This is the last concept. Pretty good concept. I think I might have gone too slow through the last section. Sometimes there are choices, right? We see this in some of the structures that we've made. So let's do ozone real quick. O3. So 3 times 6 is 18. We have a lot to go, so we're not done yet. So 18 valence electrons. Okay. So we used up 4 in the single bonds. Okay. And so then we're going to have 14 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. This oxygen has an octet. This oxygen has an octet, but the middle one doesn't. And the middle one only needs 2 more electrons. And I've got a choice. Do I share from the right or share from the left? Well, in a sense, they look different, right? If I share this one, I make a double bond, and then I get rid of those electrons. But now the molecule looks like that. But what if I had done the other one? It would look like, and so this is what we mean by resonance. We can draw both of those structures like this. So everybody pay careful attention. And then I could have drawn it like the other way too. So I'm going to draw a double-headed arrow, and I'm going to draw it the other way. Very important concept in organic chemistry, because this stabilizes the molecule, because these electrons can actually kind of go over the whole molecule. So the idea is that these can interchange with each other. Like the molecule can be this way in its electron cloud, and then a picosecond later be like this. So it's almost like that double bond is stretched over the whole molecule, and that's stable, right? So the larger the box that the electrons can have, the lower the energy. And that makes sense, right? They don't like each other. So if you try to cram them in a smaller box, the energies go up. But if you let them have a bigger box, the energies go down. And so the resonance structure allows that double bond to kind of be across the whole molecule. And we could do the same thing with the sulfate. You know, on our sulfite, remember the sulfate, I drew the double bonds up, but I could have drawn them sideways. Or I could have drawn them like this, or like this, or like this, or like that. So I had lots of options for the sulfate, formal charge, reduction, Lewis dot structure, and all of those, the positions of the double bonds are the only thing that changed, and that means they're all resonance structures. So this idea of resonance means all you're doing is changing the locations of the double bonds. You're not changing the atoms that have double bonds or the places of the atoms. You're just moving the double bonds around the molecule, and that's what gives you the resonance structures. I'm sad we didn't get to the organic structures, but these are, it's in the video here, these are the different structures for these different organic pieces. We'll have to cover that next time. Okay. And then there's a forensic application. When we learn what a hydroxy is and an acid group, you have things like gamma hydroxy butyric acid, and so there's, you know, sort of using some of these terms to come up with the name for that molecule. So, all right, so we'll see you next time.